Hello friends. So today we are going to discuss the questions, and the questions are from the year 2018 and from 2019. From 2018 there are a total of 4 questions, and it will be from the mains as well as advanced. Whereas from 2019 there are 11 questions and all are from the mains. So in total there will be 15 questions. So in the first question that was asked in the 2018 mains, and it states that the angular width of a central maxima in a single slit diffraction pattern is 60 degree. The width of the slit is 1 micrometer. The slit is illuminated by a monochromatic plane waves. If another slit of same width is made near it, Young's fringes can be observed on the screen placed at a distance of 50 cm from the slits. If the observed fringe width is 1 cm, what is the slit separation distance? That is the distance between the centers of each split. So here we are given that the angular width is given as 60 degree, and based on this we can just draw a approximate figure for that. And suppose this is our central position and this is a screen, and around the central position we are going to have a maxima, so which will be something like this, and from here we can draw the angular displacement. So this angle will be of theta, and capital D is the distance between the screen and the monochromatic source. Okay. And okay. So we are given that the angle is given as the width of central single slit is 60 degree. Okay, so theta is given to us a 60 degree, and the width of each slit is given as 1 micrometer. Okay. And fringe width is said to be 1 centimeter, and the distance of the screen is given as capital D, that is also 50 centimeter. We have to find out the split separation distance, that is small d. Okay. So the parameters that are given to us, we are given as theta, that is 60 degree, and width of each split, let us suppose that is given as A, which is our 1 into 10 to the power minus 6 meters, and fringe width, that is a beta, is given as 1 into 10 to the power minus 2 meters, and capital D, screen distance, is given as 0.5 meters. And we can say the angular width of the central maxima we can use that the angular width of central maxima which is given as theta, and this will be equal to twice of theta 1. Okay. So theta 1 is our individual angles. This will be our theta 1 and this will be also our theta 1. And we know that our theta 1 is our sine inverse of lambda divided by A. So we can find out theta 1. So theta 1 will be equal to theta upon 2, giving us 60 upon 2, which is equal to 30 degree. Therefore, we can write that our wavelength lambda will be equal to A sine times of theta 1. So we substitute the value, get lambda. A is our 1 into 10 to the power minus 6, and here we have sine of 30, which is 1 by 2. So this gives us 5 into 10 to the power minus 7 meters. Now we can use the fringe width formula, that is beta, and beta is equal to lambda capital D upon small d. So small d will be equal to lambda capital D divided by beta. Lambda we just found out is 5 into 10 to the power minus 7, and our capital D is 0.5, and beta is 1 into 10 to the power minus 2. So this gives us that the D, separation between the slits, will be equal to 25 micrometers. So option number B is the correct one. Option B is correct. Next question. It was asked in the year 2018 mains, and it states that unpolarized light of intensity I passes through an ideal polarizer A. Another identical polarizer B is placed behind A. The intensity of the light beyond B is found to be I by 2. Now, another identical polarizer C is placed between A and B. The intensity beyond B is now found to be 1 by 8. Okay. The angle between the polarizer A and C is equal to, so it has to be I by 8, not 1 by 8. So in this case, we have two situations. One is when there are two polarizers A and B, and the final intensity is I by 2. And when there is a three polarizer A, C and B, the final intensity is I by 8. So we can start that our initially we have two polarizer A followed by B, and this gives us that final intensity is equal to I by 2. And then we have, you can say, modified. Here we have A followed by C, and that is followed by B, and it is given that the final intensity in this case is equal to I by 8. And so this is our, you can say, two setups. So first of all, let's try to understand the basic intensity relationship. So in the basic intensity relationship, whenever unpolarized light passes through a single polarizer, the intensity becomes half of that, and if that is at angle of theta, then intensity becomes a cos square of theta and multiply by its intensity. So we know that when we have when unpolarized light passes through a single polarizer the intensity if given as I1, then this I1 is equal to I by 2, and in the second case, if this I1 passes through another polarizer at an angle of theta, and when light of intensity passes through intensity I1 passes through a polarizer at angle theta, the intensity if given as I2 will be equal to I1, and we have cos square of theta. So we are given, we have two, first case A and B. So we have case 1 where we have A and B, and it is said that light intensity passes through an ideal polarizer A and another identical polarizer B placed behind A. The intensity beyond A is found to be I by 2. So you can say that we have after A, the intensity is our I by 2, and after B, and which is not given at what angle it is aligned. Okay. So you can say after B, which is aligned at unknown angle theta from A, then we can say its output, that is I2, will be equal to our I by 2, and we have cos square of theta. But we are given that after B the intensity is still I by 2. So we are given, but intensity after B is our I by 2. Therefore, we can equate, which basically means that our I2 should be equal to I by 2. So, if we equate them, we get that I by 2 is equal to I by 2 cos square of phi. This gives us that cos square of phi is equal to 1, or we can say our phi is equal to 0. Okay. So it means both A and B are aligned with respect to polarization, we can say same polarization direction. So we can say A and B are aligned with same polarization direction. Now let us come to case 2. And here it is our A, then goes to C, and then goes to B. And the intensity is, final intensity is I by 8. Is I by 8. Okay. So after A, intensity, let us suppose, is I1, which will equal to I by 2. And after C, that is angle theta with A. Then after C, let us suppose that is of I2. Then I2 will be equal to I by 2 cos square of theta. And then is our, we can say, B. After B, and we can say that it is at an angle theta with C. So which comes as our I3 will be equal to I2 cos square of theta, and we substitute our I2, we get our I3 will be equal to, this is I by 2, and we get this as cos 4 times theta. Okay. But we are given that I3 is equal to I by 8. So we are given that final intensity, which in this case is I3, is equal to I by 8. So this will be equal to our I by 2, and we have cos 4 of theta. And we can just solve it now, and this gives us that cos 4 of theta is equal to, I goes with I and 2 goes by 4. So this comes as 1 by 4, and our cos of theta will be equal to 1 square root of 2, giving us theta is equal to 45 degree. So the angle will be, D is our, we can say, 45 degree. So option D is correct. Option D is correct. We come to the next one, which was asked in their 2088 advance, and it states that a wire is bent in the shape of a right angle triangle and is placed in front of a concave mirror of focal length f as shown in the figure. Which of the figure shown in the 4 options quantitatively represent the shape of the image of the bent wire? These figures are not according to the scale. Okay. So in this case, so this is a figure, we have concave mirror, and the mirror and the wire which is placed exactly at f by 2 and f, and it is shaped in the right angle triangle. Okay. And where the angle at the f is given as a 45 degree. So we are given that one end of the wire is at a distance of f, whereas the other end of the wire is at a distance of f by 2. So we can use to find out the image of respectively these 2 points. One will be at f and another one is at f by 2. So we can use the standard formula, that is our 1 upon f is equal to 1 upon v plus 1 upon u. And here we are going to find out what will be our image. Okay. So first case, we consider that you can say, let me name the triangle, let us call this A, B and C. Okay. So we can say for point C, so for point C, we are given that our distance of the object, that is u, will be equal to minus of f, and the focal length will be equal to minus of f. So here we can find out our you can say position of the image. Let us call this as v of f, and we can call this as that v is equal to v of f, which we are supposed to find out. So we substitute, we get minus 1 upon f is equal to 1 upon v of f, and this also comes as minus 1 upon f. So this gives us that v of f will be equal to infinity. Okay. So it means the image corresponding to point C will be somewhere at infinity. Okay. Now we come to the point B. So you can say for B, we have our u is equal to minus f by 2, and our focal length will be same, minus of f, and our position of the, you can say, image, let us call that vf by 2. So we substitute in the same formula, we get this as 1 upon minus, and we have here 1 v for f by 2, and this will be minus, and we have this as f by 2. Sorry, 1 upon f by 2. 1 upon minus f by 2. And this will be plus. So this gives us that the position of the image for the point vf by 2 will be coming as f. Okay. And we can also find out the magnification. That will be quite easy, because of magnification we know that magnification for the point f will be equal to minus v upon u, that is a standard formula. We have it is vf is our vf, and u was in f, u was at minus of f. Okay. And vf we just found is of infinity, so we get the magnification of the focal of the point which lies at f is equal to infinity. Okay. And for the second part, magnification for f by 2, once again it will be minus of v upon u, and this comes as, we found it as to be f upon minus of f. This will be coming as, sorry, f by 2, and this will be coming as 2. So magnification will be twice. So therefore the approximate figure is our D is the correct option. Option D is correct. Okay. We come to next question. It was also asked in the year 2018 advance, and it states that the sunlight of intensity 1.32 kilo per meter square is incident normally on a thin convex lens of focal length 20 centimeter. Ignore the energy loss of light due to lens and assume that the lens aperture size is much smaller than the focal length. The average intensity of the light in kilowatt per meter square at a distance of 22 centimeter from the lens on the other side is. In this case, we are given that the sunlight of intensity is incident on the normal of a convex focal length. Okay, so we can just draw an approximate figure for that. And suppose this is our convex lens, okay, and we have a principal axis, and because the sun is very far, so light rays will be coming almost parallel. So they will be coming almost parallel to it, and they are probably going to converge at a point which will be nothing but the focal length. Okay, and the focal length is given as 20 centimeter. So they should be converging at a point of 20 centimeter. But we have to find out the intensity at a distance of 22 centimeter. So we can mark that this 22 centimeter will be somewhere here. And so obviously we can see that at this particular point there will be some kind of small, you can say, bright spot. Okay, small spot will form because we are interested in this particular point, intensity at here, that is our 22. And so it means we are going to find out the energy at 22 centimeter, average intensity at 22 centimeter. So it means this is our convex lens. We can say that for convex lens, focus is parallel rays to its focal point, okay, and to its focal point means at 20 centimeter. But we are asked that to find average intensity at 22 centimeter, which is 2 centimeter beyond the focal point. So it means after passing the focus, the rays are going to diverge again. You can say thus the rays diverge again, forming a small spherical bright spot, Therefore, we can say, or we can just write a general formula for that. We need average intensity at 22 centimeter. Average intensity at 22 centimeter will be equal to power collected by the lens. Power collected by lens plus area over which it spreads at 22 centimeter. It is not plus but divided by area over which it spreads at 22 centimeter. So it means basically we are mainly interested in the area of the lens as well as the area of the spot. Okay. So let us find out what will be the power collected by the lens. Say power collected by lens. If given as P, then this P will be equal to our I naught multiplied by A, where A is the, you can say, area, aperture area rather, aperture area, and this I naught is given to us, so we can substitute the value. We get P will be equal to, this is 1.32 and times A. So this is power collected by the lens, PL. Now similarly, we are going to find out what will be the, first of all, the area of this 22 centimeter, and for that we require the radius. So we can say that the divergent beam radius and let us suppose that is given as r prime, then this r prime will be equal to 2 divided by 20 multiplied by r. Okay. So this gives us that our r prime is equal to 0.1 times r. Okay. Now we can find out the area. So we can say the area of the spot, let us call that A prime will be equal to pi, we just found out its radius, and square. So this comes as 0.01 pi r square, and this pi r square is the area of the lens. So it comes as A prime will be equal to 0.01 times A. Now we can find out the average intensity. So you can see average intensity that is our I will be equal to P divided by A prime. P we just found out is 1.32 times A, and A prime is our 0.01 times A. A and A cancels out, and we get that the intensity I will be equal to, it will be coming as one second. Yeah. So it is our 1.32, and this is our 132 kilowatt per meter square. Okay. This is our average intensity. Next question. It was asked in the 2000 mains, 19 mains rather, and here it states that a concave mirror has a radius of curvature of 40 centimeter. It is at the bottom of glass that has a water filled up to 5 centimeter. If a small particle is floating on the surface of water, its image as seen from directly above the glass is at a distance d from the surface of water. The value of d is close to. The refractiveness of water is given as 1.33. So in this case we have particle, and this particle on the bottom we have a, you can say, concave mirror. This is a concave mirror, and we have to find out when it is seen from the top, it is at a distance d from the surface of the water. So we have to find out this value of d. Okay. So we can just draw an approximate figure for that. And we have an observer. So let us suppose this is our observer. And this is our particle. And the particle here, it is our, you can say, the mirror. And the height is given as 5 centimeter. And this particle is completely inside the water. Okay, this is completely inside the water, and this is given as 5 centimeter. And we are given the radius of curvature is 40, and the focal length we can easily find out from there that will be our 20 centimeter. Okay. So we are given that we have a radius of curvature, that is our r, it is given as 40 centimeter. So from here we can easily find out our focal length, that will be equal to r by 2, that will be coming as 20 centimeter. Okay. And this will be our negative. And u is given to us, the distance of the object or particle from the lens is our u, and that will be equal to our minus of 5 centimeters. So u we are having minus of 5. So we can find out the position of the image, that is our v, and we can say our 1 upon v plus 1 upon u is equal to 1 upon f. So this gives us that 1 upon v is equal to 1 upon f minus 1 upon u. 1 upon f is our minus of 20, and we have u as minus 5, so this becomes 1 upon plus 5. So this gives us that our v will be equal to 20 by 3 centimeters. So it means that the image position will be somewhere here. Okay. So this is our 20 by 3 centimeters. And from the particle, let us suppose this distance is our h. So therefore we can write, and this image, okay, let us call this as image I. So this image I will be acting as an object for the refracting surface, because the observer is just above the water. Okay, so light rays will be refracted by this surface of the water. You can say this image that is of eye acts as a object for light getting refracted at the water surface. Refracted at water surface. So we can find out the, you can say, the total distance of this image from the water surface, which is our h. So you can say h will be equal to 5 plus 20 divided by 3, which comes as 35 divided by 3 meters. Okay. And this will be appearing as a, you can say, apparent, which is asked in the case of D. So we can say our apparent height will be equal to our real apparent distance is equal to real distance divided by mu, and apparent distance is in this case is d, real distance is our, you can say, 35 by 3, and mu is given as 1.33. So this gives us a d will be close to 8.8 centimeters. So this is our apparent distance AD. RD is our real distance. So this comes as 8.8. So option number C is the correct one. Option C is correct. So we come to the next question. It was asked in the year 2019 mains, and it states that a concave mirror for face viewing has a focal length of 0.4 meter. The distance to which you hold the mirror from your face in order to see your image upright with the magnification of 5 is. So in this case we are given the focal length and the magnification. So in this case we are going to use two formulas. One is a mirror formula, another one is a magnification formula. And the magnification is going to give us the image, and that is a V, and then we are going to solve it further by using the you can say the mirror formula. So we start with the magnification. So we are given the magnification which is our minus V upon U, and it is given as 5, and this is minus V upon U. So we can say our V will be equal to minus 5 times U, and then we can use the mirror formula, and there we get 1 upon F is equal to 1 upon V plus 1 upon U. Focal length is given to us, so we write it 1.4 is equal to V, we just found out is minus of 5 times U and plus 1 upon U. So if you solve it, we can get that the value of U. So this gives us that the value of U will be equal to 0.32 meters. So option number C is the correct one. Option C is correct. Next question. It was also asked in the 2019 mains, and it states that a point source of light S is placed as a distance L in the front of the center of plane of mirror of width D, which is hanging vertical on the wall. A man walks in front of the mirror along a line parallel to the mirror at a distance 2L as shown below. The distance over which the man can see the image of the light source is in the mirror is. Okay. So this is, we can say, more or less related with the, you can say, triangles, because once we draw the complete figure we have to solve it using the triangle. So for that, let us draw an approximate figure, and you can say that so we have the light coming from the source S in this direction, and it will be traveling somewhere like here, striking the, you can say, the path, and same with the opposite side also. And let us name them. We call this as A, and this is a B, and then we have, let us join them. So we have our C, then it is D, and we have our E, and we have our F, then comes a G, H, I and J. So we have to find out total G, J. Okay, we have to find out Gj, and in this case we already know the distance between Hi is our capital D, small d rather. So we are mainly interested in finding out the distance Gh, and that Gh will be equal to these two will be same. And for that we can use our, you can say, the triangle property, and we are given that AB is a D or Hi is same. Okay, so we can say that our AB is equal to Hi, and from here we can write that our ds, which will be equal to our CD, is equal to d by 2, and these two are equal to d. Okay. And also our AH will be equal to twice of AD. So this gives us that our GH will be equal to twice of CD, which giving us that twice multiplied by d by 2, which gives us d. Okay. So we just found out our GH, and similarly we can say that our Ji will be also equal to d. Now the total distance, that is our Gj will be equal to Gh plus Hi plus Ij, and that is d plus t plus t, which gives us that our Gj will be equal to 3 times d. So we have option number C is the correct one. Option C is correct. And come next question. It was also asked in the 2019 mains, and it states that plane mirrors M1 and M2 are identical to each other such that the ray of light incident on mirror M1 and parallel to the mirror M2 is reflected from mirror M2 parallel to mirror M1. The angle between the two mirrors is. So we have two mirrors at an angle, let us suppose theta, which are, so this more or less can be also solved by using simple concept of parallel lines. So this is angle theta, and we have a mirror M1, and this is mirror M2, and it is said that the light ray incident on M1 is parallel to M2. So we can just draw incident light ray on M1, which is parallel to M2, and here we can just draw our normal, and it is going to strike the mirror M2, and after that it is given that the reflected ray from M2 will be coming parallel to M1. So it will be moving in this direction, that is parallel to our M1. So this is our A, B, C, and let us suppose this is our D. And we have our AB. AB is parallel to M2, and we have our CD is parallel to M1. So these two things are given to us. Now we can easily use the property. So angle, this is let us suppose O, and we are given that angle M1 O M2 is equal to theta, but we have that our AB is parallel to M2. Therefore, we have our angle M1 BA will be equal to theta. So we get that this angle is also equal to theta. And if this angle is equal to theta, then this small angle will be equal to 90 minus theta, because this entire angle is of 90 degree, okay, because this is our 90. So this is 90, and we get this angle will be our 90 minus theta. So other angle will be also 90 minus theta, and therefore this angle will be also equal to theta. Okay. So therefore we can say that our angle OBC will be equal to theta. And similarly, we can write, we can say that our CD, we have parallel to M2. Therefore, we are going to get that our angle DCM2 will be equal to theta. So we have this angle theta. Similarly, this angle will be also theta. So from here we can say that angle BCO will be also equal to theta. Now we can use the triangle property. Triangle is our BOC. We have triangle BOC, which is our theta plus theta is equal to 180, giving us theta is equal to over 60 degree. So the angle between the mirrors is of 60 degree. That the option number D is the correct one. Option D is correct. Next question. It was also asked in the year 2019 mains, and it states that a transparent cube of side D made of material of refractive index mu2 is immersed in a liquid of refractive index mu1, which is less than mu2. A ray is incident on the face AB at an angle theta shown in the figure. The total internal reflection takes place at point E on the face BC. Then theta must satisfy. Okay, so basically we have a transparent cube, and that transparent cube is inside a, you can say, liquid of refractive index mu1. So we are, and total internal reflection is taking place. So we can use the concept of this TIRF, total internal reflection. So let us draw an approximate figure first of all. And for that we are only interested in two sides. One side is AB and another side is our, so this is A, B, and we are interested in E. And we have angle of incident that is given as theta. And it gets refracted to point E, and then total internal reflection. So let us suppose this angle is our R. So this angle will be 90. So we are going to have this angle will be our 90 minus R. So we can use Snell's law on the face AB. Snell's law, let us call this as point as P. At P, refractive index is given as mu1 and this is our mu2. Snell's law P, this gives us mu1, we have sine of theta is equal to mu2, sine of r. And from here we can write that our sine of r will be equal to mu1 upon mu2, and this is our sine of theta. And the angle of incident at E is our 90 minus r. Angle of incidence at E, it is our 90 minus r. So for total internal reflection at E, total internal reflection at E, this angle, that is our 90 minus r, should be greater than or equal to critical angle, that is our C. Okay. And critical angle is nothing but sine inverse of mu1 upon mu2. So we substitute, we get 90 minus r should be greater than or equal to sine inverse of mu1 upon mu2. And we just try to make some, and sine of r we just found out, we substitute it here, we get this as 90 minus mu1 upon mu2 sine of theta is greater than or equal to sine inverse mu1 upon mu2. Sorry, I have to find out r, not sine. So we can just, so from here I get my r is sine inverse, that is mu1 upon mu2, and this is sine of theta. So we substitute it, value of r, this gives us 90 minus, and here we have sine inverse. Okay, sine inverse of, yeah, this is correct now. And we can just try to modify it, and we can write it 90 minus sine inverse of mu1 by mu2 is greater than or equal to sine inverse of mu1 by mu2, and here we have sine of theta. And which can be further written as, we can write this as sine of 90 minus sine inverse of mu1 upon mu2 greater than or equal to mu1 upon mu2, and this is our sine of theta. Sine of 90 minus will be equal to cos. So we get this as cos of sine inverse mu1 by mu2 greater than or equal to mu1 by mu2, and we have sine of theta. And we can write this as 1 minus mu1 upon mu2 whole square, and its square root is greater than or equal to mu1 upon mu2, and this is sine of theta. Now it is a simple calculation, most of things are done, and this we take LCM, mu2 and mu2 goes away, and we get this as mu2 square minus mu1 square, and its square root is greater than or equal to mu1 sine of theta. So we can write that our sine of theta is less than or equal to, this comes as 1 upon mu1, and this we have mu2 square minus mu1 square. theta will be nothing but its inverse, is our sine inverse 1 upon mu1 square root of mu2 square minus mu1 square. So this is the value of theta. Okay, so the option, okay, they have taken the ratio, so we can just modify it. So obviously option number C will be the correct one. So only thing left is they have taken the ratio. So we can just write it. Theta is less than equal to sine inverse, and here we get mu2 square upon mu1 square minus 1 and its square root. So option C is correct. Option C is correct. Next question. It was also asked in the 2019 mains, and it states that a ray of light AO in vacuum is incident on a glass slab at an angle of 60 degree. The refracted angle at 30 along OB as shown in the figure. The optical path length of light ray from A to B is. Okay. So here we have refractive index, so we have to find out the optical path length, and the optical path length will be AB plus mu times our OB. That will be optical path. So you can write the optical path is equal to, we have our OA plus mu times OB. Okay. And we can find out our refractive index. We have angle of incident and angle of refraction. So we can say, let us suppose at O we can use Snell's law. Snell's law at O, this gives us that our mu1 sine of I is equal to mu2 sine of R. Mu1 is our 1 and I is our 60, mu2 is our mu and sine of R. So we write here sine of 60 divided by sine of 30, and this is equal to value of our mu2, which comes that mu2 is equal to square root of 3. Okay. And for AO, we can use the trigonometric, you can say, identity. And if we extend in this way, so this length will be also, see, this height will be also our A. So we can say our AO will be equal to A and divided by cos of 60. Okay. Similarly, we can do for this will be our B. Similarly, we can do for B also. So we can say our AO will be equal to A divided by cos of 60, which is nothing but our 2A, and our OB is equal to B, and here we have cos of 30, okay, and that will be equal to 2 by root 3 times B. So we can say that our optical path will be equal to 2A plus root 3 multiplied by 2 root 3 times B, and here root 3 goes away, so we have left with only 2A plus 2B. So option number C is the correct one. C is correct one. So go to the next question. Okay, it was same, sorry. It was asked in 2019 mains, and it states that in the figure, the optical fiber length 2 meter long has a diameter of d as 20 micrometer. If a ray of light is incident on one end of the fiber at an angle of theta 1, that is 40, the number of reflection it makes before emerging from the other side is close to. The refractive index of fiber is 1.31 and sine of 40 is given as 0.64. So the total length of this fiber is given as 2 meters. So it means after suppose n number of reflections, the total distance it can travel will be equal to over 2 meter. So we are going to find out what will be the distance being traveled in one reflection. So we are interested in this distance. Okay. We already know our theta 1. We can find out theta 2 by using Snell's law. And let us suppose this point is our A. So we can Snell's law at point A, and let us call this as X. Snell's law at X will be giving us mu 1 sine of theta 1 is equal to mu 2 sine of theta 2. Theta 1 is 40, mu 1 is 1, and so from here we get our sine of theta 2 is 1 upon mu 2, and refractive index of is given as 1.31, and we have this as sine of 40, which comes 1.31 sine of 40 is 0.64. So from here our theta 2 is approximately equal to 30. So we found out 30, and this distance is by x, we just assumed it, and this height is given as d to us. Okay, so we can easily find out that tangent of 30 tan of 30 will be equal to d upon x. So we can say our x is equal to square root of 3 multiplied by d. So in one reflection we are able to cover this much distance. Let us suppose there are n number of reflections. So we can say for n number of reflections, we can write that our total length is of L. So you can say our for n number of reflection, we can say our n multiplied by x should be equal to L. So therefore our n will be equal to L upon x, and length is given to as 2 meter. X we found out is root 3 and divided by d, and d is given to us as diameter is 20 micrometer. So this is 2 into 10 to the power minus 6, and this n is approximately equal to 57000. So option number D is the correct one. Option D is correct. So we come to the next question. Okay, so in this question it was asked in the year 2019 mains, and it states that one plano-convex lens and one plano-concave lens of the same radius of curvature r but of different materials are joined side by side as shown in figure. if the refractive index of the material of 1 is mu1 and that of 2 is mu2, then the focal length of the combination is. Okay, so we have the figure. So we have combination of two lenses. So this is your first lens. Okay, and we have this is a second lens. And their radius of curvature are given as same, and we need to find out their focal length of combination, which will be a focal length of first as well as plus the focal length of second. Okay. So let us, we can just redraw the figure separately. So this will be our first lens and this will be our second lens. So this is lens 1 and this is lens 2. The refractive index is given as mu1, this refractive index is given as mu2. Okay. And for the first lens, you can easily see that for this plano-convex lens, our radius of curvature R1 will be equal to R, whereas R2 will be equal to infinity. Okay. So you can say for lens L1, for our L1, our R1 is equal to R and our R2 is equal to infinity. And the formula is quite straightforward. Let us suppose it is called 1 upon F1 will be equal to refractive index mu1 minus 1, and this comes 1 upon R1 minus 1 upon R2. We substitute R2 as infinity, and this gives us that our F1 will be equal to R divided by mu1 minus 1. Similarly, we write for our L2. So we can say for L2, we are having it as R1 is equal to minus of R and our R2 is equal to infinity. So same formula but a different focal length. F2 is equal to refractive index is also given as different. So this comes as 1 upon R1 minus 1 upon R2. We substitute the values, we get the F2 is equal to, this will be coming as R1, sorry, not R1 but R, and this will be equal to, oh sorry, my mistake. Here we have to, one second, this is minus of R, yeah, this is correct. This is minus, yeah, this is our mu2 minus 1. So we found out the individual focal length. So combined focal length will be simple, that 1 upon F is equal to 1 upon F1 plus 1 upon F2. So we substitute 1 upon F1, that will be equal to our mu1 minus 1 divided by R, and this comes as minus mu2 minus 1 divided by R. So we take the LCM, this comes as mu1 minus mu2 divided by R. So therefore the focal length F is equal to R divided by mu1 minus mu2. So we have R mu1 minus mu2, that option D is correct. Option D is correct. So we come to the next formula, next question rather. And it was asked in the 2019 mains, and it states that a thin convex lens L, refractive index 1.5, is placed on a plane mirror M. When a pin is placed at A such that O is 18 cm, its real inverted image is formed at A itself as shown in figure. When a liquid of refractive index mu1 is put between the lens and the mirror, the pin has to be moved to A prime such that OA prime is 27 cm to get its inverted real image at A prime itself. The value of mu1 is equal to. So we can divide this question into two parts. One is without the liquid and another one is with the liquid. Okay. So let us draw the figure. First of all, that is our without liquid. This is a plane mirror and we have a lens, and you can see the object and image at the same position, that is of A. So here it is A, and both the object as well as the mirror at the same position, and in this particular case the height is given as 18 centimeter. So let us suppose this is our O. So this height is given as 18 centimeter. Okay. Similarly, for when we are having liquid, now in this case there is a liquid is put between here. So we are having a liquid here, and now the position is moved to A prime. Okay, so this is our A prime, and once again they are both image and object are matching with each other, and distance is given as 27. So we have to find out the refractive index if it is asked for mu1, which we are supposed to find out. So we are going to use the, you can say, lens maker formula for both the cases. In the first case it is given as 1.5, which will be same for both the cases. So let us suppose this is case 1 and this is case 2. So we have for case 1, and we can write this as 1 upon f is equal to mu minus 1 and 1 upon r1 minus 1 upon r2. And the image and it is placed at same 18. Okay, 18 is there, so we can write it 1 upon f1. Refractive index is 1.5 minus 1, and we get this as 1 upon 18 minus 1 upon 18. Sorry. And this gives us that our 1.5 is our 0.5, that is 1 by 2, and this comes as, so you can say 1 upon f1 will be equal to 1 by 2, and this comes as 2 upon 18. So 2 and 2 goes away, so we get that our f1 is equal to 18. Okay. And for the second case, for case 2, we are going to get that the refractive index we need to find out. So we just formulate the equation that f2 is equal to mu1 minus 1, and this comes as, because one of the, you can say, r2 will be equal to infinity in this case, so we get it as 1 upon minus of 18 and 1 upon infinity. So we get this as 1 upon f2 will be equal to, we have this as mu1 minus 1 and divided by minus of 18. So the total focal length, here we are mainly interested in, okay, 1 upon f1, that is equal to 1 upon 18. So the combined focal length for case 2, we can write 1 upon f is equal to 1 upon f1 plus 1 upon f2. So this is 1 upon 27, and 1 upon f1 we found out is 1 upon 18, and here it comes a minus of mu1 minus 1 divided by 18. So we can easily sort it now, and this gives us that we can take 18 as LCM, and this comes as 18 upon 27 is equal to 1 minus mu1 plus 1. So this comes as 2 minus mu1, which gives us that mu1 is equal to 2 minus 18 upon 27. And 18 upon 27 is basically, you can see this goes by 9, 2 and 9, 3. So we can write this as our mu1 is equal to 2 minus 2 by 3, which is 6 minus 2 divided by 3, which gives us that our mu1 is equal to 4 by 3. So the option is C is the correct option. Option C is correct. Next question. It was also asked in 2019 mains, and it states that a convex lens of focal length 20 centimeters produces images of same magnification 2 when an object is kept at two distances x1 and x2, where x1 is greater than x2 from the lens. The ratio of x1 and x2 is, so we have two position of object, but the magnification is same. Okay, and the focal length is given to us at 20 centimeter. Okay. And we are given that our x1 is greater than x2. Okay, and for we can say, first of all, we are going to you can say solve it for when the object is at a distance x1. Object is at x1, and basically it is a real image, and therefore we can write that our m is equal to 2, which is our v by u, and u, like we said, is our x, so we can write this as v upon x1, which gives us that our v will be equal to 2 times x1. Now we can use the simple formula of the focal length, that we have 1 upon f is equal to 1 upon v plus 1 upon u. Focal length is given to 20, so this comes as 1 upon 20 is equal to v is 2x1 plus x1. So this gives us that our x1 is equal to, this comes as 60 and 30 centimeter. Now we find out for x2. So we can say object we have the object at x2, and this is a virtual image. So for that case, we have a magnification minus v upon u. This is 2 is equal to minus v upon x2. This gives us minus of x2 rather, and this gives us that our v will be equal to 2 times x2. Same formula, you can write that this will be equal to 1 upon 20 is equal to 1 upon 2x2 minus 1 upon x2. This gives us that our x2 is equal to 10 centimeters. And we can find out a ratio, and that is our x1 upon x2. x1 is our 30, x2 magnitude only, that is our 10. This comes as 3:1. So option number D is the correct one. Option D is correct. So we come to the next question, and it was also asked in the year 2019 mains, and it states that what is the position and nature of image found by the lens combination as shown in the figure, where f1 and f2 are the focal length. So we have two lenses here. One is convergent lens, another one is a divergent lens. Okay. So let us call this as lens L1 and this is lens L2. So the image that will be found by lens L1 will be acting as an object for lens L2. First of all, we are going to find out the image because of lens L1. You can say for L1, we can write that our 1 upon V minus 1 upon U is equal to 1 upon F. Focal length is given as 5. So we get 1 upon V. This is minus of minus 20 because a ray of light will be traveling in this direction and distance is measured with respect to pole in the opposite direction. And this will be equal to 1 upon 5. So this gives us that V is equal to 20 upon, let me solve it. So we get this as 1 upon V is equal to 1 upon 5, and this comes as minus 1 upon 20. Okay. And we have the LCM as 100, so this comes as 20 minus 5, which will be coming as 15 upon 100. And we can solve it by 5, so this comes as 5/3, 520. Yeah, so this is good now. So we have our V is equal to 20 divided by 3. Now this will be acting as object for second lens. So we can, this will act as object for L2, and the distance is, you can say it will be towards the right of the L1, right of L1, that is 20 by 3. So now we are interested in the position of the, you can say, object. Okay, so somewhere it will be here, let us suppose. Okay, so this is our image I, and this image I will be acting as an object for lens L2. So we are interested in this distance, so that will be equal to our 20 by 3 minus 2. This is 20 by 3, 2 centimeter. Okay, this is 20 by 3 centimeter. 20 by 3 centimeter is something 6. Okay, it will be somewhere else. 1 second. So we can say that the image will be 20 by 3, and this 20 by 3 is approximately equal to, this will be our 6 point something. Okay, so we can say that the image will be somewhere here. So this is I, and this total distance is our 20/3. 20/3. But we are only interested in this much distance because this is our object distance. So this will be equal to 20/3 minus of 2, which will be equal to 14/3. This looks good now. So you can say that object distance for L2 will be equal to 20/3 minus 2, which comes as 14/3. So once again, same formula, 1 upon V minus, and this is 1 upon 14/3 is equal to, focal length is given as, it is given minus of 5. So this becomes minus of 5, and we get from here that 1 upon V is equal to minus 1 upon 5 and plus 3/14. And we can take the LCM, and our LCM will be equal to, this will be, LCM will be equal to 70. So this comes as 14, and we have, this is minus 14 and plus 15. So from here we can say that our V will be equal to 70 centimeters. So 17 centimeters to the, you can say, right of point B, because it is positive. Okay. So to the right of B, it will be somewhere here. That is our I1, that is a final image, and it will be at a distance of 70. So we can say that 70 centimeter from point B at right and real, and real. So the option number B, right and real, option number B is the correct one. Option B is correct. I think this completes all the questions. Yeah. So this completes all the questions. So in this, we did for 2. One was from the year 2018, total of 4 questions. And these 4 questions, there were some from mains and some from advanced. Whereas from the year 2019, there were only 11 questions, and all of them from mains question. This completes all 15 questions. Thank you.